Okay, moving on. We need to introduce a new concept known as the gravitational field of a point mass. So we now need the equation that can help us find gravitational field strength, or the gravitational field to be more general. So we need to remember that gravitational field strength or gravitational field is essentially the force per unit mass, right? And it's possible for us to derive an equation for this specific quantity. Now, first we need to understand what the definition actually is. So we've already defined a gravitational field strength as the force per unit mass. So essentially the force, which is F, per unit mass, which is M. Okay. So now we need to know what the gravitational force between two masses actually is. And we know that. We know that F is equal to gmm over r squared. So our goal is to combine these two equations to get one equation for the gravitational field strength. So if we combine these two equations, which is essentially placing our value of force over here, okay, as you can see, we've placed our value of force over here, and we've placed the mass at the bottom over here. Okay, so that m and that m will cancel, and finally we'll be left with g being equal to gm over r squared. So we now want to introduce a new concept known as acceleration due to gravity. It's almost similar to the value of g, but just a little bit different, and I'll explain why that is. If we assume that the Earth is a uniform sphere of uniform density, we can therefore apply the equation that we previously derived, which is g is equals to gm over r squared. Okay, so the radius of the Earth, as we know, is approximately 6.4 times 10 to the power of negative 3 kilometers. If you didn't know, now you know. Okay, so let's assume you want to move a few kilometers above the Earth's surface. So you're at this point over here, okay, and you want to move to this point over here. So you're at this point over here, and you want to move to this point over there. So what's going to happen is you're going to move a certain distance h, okay, and that distance h is going to be the additional distance that you're going to move. So the total value of the radius itself, remember this value of r, which we have over here, measures from, if you have one object, measures from the center of that object to where the mass that you want to find its force is at. So if you have a person over here, the value of this r, right, which is over here, is essentially this distance, right, from the center itself. Okay, so it's important for you to just be thinking about that. So essentially, if we now add that value of h, so the general formula at height h will now be equal to gm over r plus h squared. Now, you can see that h is approximately smaller than r. So the h that we're talking about, maybe you've moved 200 meters, right? You can see that if the Earth's radius is about 6,400 kilometers, moving 200 meters won't really change the value of r that much, right? So since h is very small to r, we can therefore say r plus h will be approximately equal to r squared. So it doesn't change that much. So a simplified version will still go back to being g is equals to gm over r squared. Why am I saying this? This is very important because we now want to see, or we can see that for small distances above the Earth's surface, g can be assumed to be approximately constant. And we can call it the acceleration due to free fall above a certain point in the Earth's surface. We can say that any object that's falling will fall with the acceleration due to gravity, which is equivalent to g. Why am I saying this? Because look at this. Look at this little derivation that we're going to do over here. Okay, so essentially we know that F is equal to ma. Okay, right? And the force per unit mass is going to be the acceleration. But the value of g, as we've defined it, is actually the force per unit mass. Okay, but the value of g is actually the force per unit mass. So I can safely say, hey, A is equal to g. Okay, so the gravitational field strength will actually be the acceleration due to free fall when you're at a certain distance above the Earth's surface. As you get above that, the value of g would then change. It's no longer constant, which is 9.81. But for now, acceleration due to free fall will remain as 9.81. So A question can ask you, explain why G is approximately constant above the Earth's surface with reference to field lines. And how you tackle this is basically saying, hey, the change in height above the Earth's surface is negligible, right? We're not going to have an insane change in height above the Earth's surface, so the field lines that you see will remain effectively parallel, right? They will not spread to show that the field strength is decreasing. What do I mean by this? So if G was not constant on the Earth's surface, right? So let's assume this is my Earth, right? If G was not constant, I was supposed to see something like this. Okay, I was supposed to see my field lines getting further and further and further apart. So you can see that these field lines are getting further and further apart. One is going this direction, one's going that direction, right? So that implies the field strength is not constant. But if your field strength is like this on the surface, like this, effectively parallel, it means it's the same throughout as you'll be going above. So if you were to zoom in, right, if you were to zoom in on the Earth's surface, you're essentially going to see, so if this is your Earth, you're effectively going to see parallel lines on the surface of the Earth, but then they become, or they start decreasing as you now get further and further away from the Earth. So as you now zoom out, you now see that, hey, they're actually diverging, but at the surface, they seem to be effectively parallel. So that's how you can see that at the close to the Earth's surface, the value of G is basically the same.